right, everybody, we are going to go over the last example from the 3.8 notes, example number 11. I already drew the picture so that way it'd save us a little bit of time. What we have is a boy running toward a street lamp at 6 feet per second. If the street lamp is 30 feet tall and the boy is 5 feet tall, when he is 4 feet from the base of the lamppost, we need to find part A, how fast is his shadow length changing, and part B, how fast is the tip of his shadow moving. So I've labeled this as the distance away from the lamppost as X, and the boy's shadow is S. Remember, when you draw a shadow, it's on the ground. It's not in the air. Your shadow is on the ground. So we are looking for how fast is his shadow length changing. So the rate at which his shadow is changing would be ds dt. Okay, so that's what we're looking for in part A. Now, you do have right triangles in this picture. But once again, just like we talked about with the cone a couple examples back, you don't want to do Pythagorean theorem with this because you're going to end up with too many unknowns, and we don't know anything about this hypotenuse. We do know that this is 30 and this is 5, and that's about it. We have a big right triangle and we have a little right triangle, and they both share this angle right here. They both also have right angles, of course. So due to angle-angle similarity, we can assume that the little right triangle made by the boy and the big right triangle made by the lamppost are similar to each other. So what I would do is I would set up similar triangle ratios and then go from there. You're going to have less unknowns, which is going to make life a little easier for you. So if we set up ratios, one of the ways we could do ratios, there's many ways that you could do this, but one way to do it would be to take the height of the lamppost over the height of the boy. So this would be 30 over 5, and then set that equal, I guess I need to put that over here, set that equal to the entire length of the big right triangle, which would be x plus s. Let me move this down a little bit for us. So this would be x plus s all over the base of the little right triangle, which would just be s, like that. All right, so now we're going to cross multiply. So 30s equals 5x plus 5s. Don't forget to use the distributive property with that. Now we are looking for ds dt, and we need to do this implicitly. So the derivative of, well, actually, let's get the like terms moved together. So I'm going to subtract 5s from both sides. So 25s equals 5x. And now take the derivative implicitly. So this will be 25 ds dt equals 5 dx dt. All right, so we're looking for ds dt. I have dx dt in my equation, and I believe that we were given some more information that I have not labeled yet. So it says that the boy is out running toward a street lamp at 6 feet per second. So that's a rate of change we haven't labeled on our picture yet. So if he is, here he is right here, he's running towards the street lamp at 6 feet per second. So if the distance between him and the lamppost is x, the rate of change is going to be dx over dt. Now he's running towards the lamppost. So that means that the distance between him and the lamppost is getting smaller. So this needs to be negative 6, and it was feet per second. Okay, that is negative because this distance is getting shorter and shorter. So now you're going to put negative 6 in, Let's see here. I'm going to come down just a little bit lower. So this will be 25 times negative 6 equals 5 times, oh, I'm sorry, I put that in the wrong spot, didn't I? This is 25 ds dt equals 5 times, put the negative 6 in here, for dx dt. So 25 ds dt equals negative 30. So ds dt will be negative 30 over 25, which is going to reduce to negative 6 over 5. And the label on that will be feet per second. So negative 6/5 feet per second. So that means that you're getting a negative rate of change for the shadow, which makes sense, should make sense. The closer that he gets to the lamppost, the more of an angle this is going to create, and the shorter his, like if he's standing, well, I guess I should make him a little shorter, huh? If he's standing here, his shadow is going to be shorter than when he's standing over here. Okay, that angle is going to change coming down from the light, and it's going to make his shadow get shorter. So a negative 6/5 feet per second is a reasonable answer for the rate of change of his shadow. So that was part A. Now, part B is asking for how fast is the tip of his shadow moving. That's kind of a weird question to ask, huh? So the tip of his shadow is right here. So to gauge how fast the tip of his shadow is moving, you have to measure it with relation to the base of the lamppost. So actually you're looking at this distance from the base of the lamppost all the way to the tip of the shadow is what that question is really asking you for. How quickly is that distance changing? So in order to find this distance, well, that distance is made up of the distance x and the distance s. So you want to find the rate of change of that distance. So we want to find the derivative of x plus s with respect to time, dt. Now, this is really nice about this. To find this, you can split this up, and this becomes dx dt plus ds dt. And we have all of that information. Actually, we just found ds dt. So that goes in and becomes negative 6/5. And dx dt was given to us up here in the given information in the problem. So that's also available. We don't have to calculate it. It's negative 6. So you put this in like that. So you have negative 6 plus negative 6/5, which is really just like negative 6 minus 6/5. Let's see, what will that be? If we put a 5 in the bottom here, this will be negative 30 minus 6/5. So that'll be negative 36/5. And that distance will be feet per second. So you're going to get negative 6/5 feet per second for the rate of change of his shadow, and you're going to get negative 36/5 feet per second for the rate of change of the tip of the shadow. And that's it for example number 11.